Good evening. I really appreciate the invitation by Dr. Dinggang Shen and Guohua Chao. Always great to meet old and new friends. The title of my presentation is Medical Imaging Research and Education at RPI. So there are two parts in this talk, research part and education part. While ShanghaiTech is the newest major research university in China, our Rensselaer Polytechnic Institute, or RPI, is the oldest technological university in North America. Indeed, RPI was established in 1824, which can be easily remembered as 2 to the power 0, 2 to the power 3, and 2 to the power 1, 2 to the power 2. Once upon a starting time, we had Rensselaer School. Now we have RPI that has been consistently ranked since 1970 among the top 50 U.S. universities. Given the fact that we have no medical school and the fact that we are very small with only 500 faculty members, I would say this ranking is remarkable. RPI indeed has a decent reputation. For example, RPI's faculty and alumni include one Nobel Prize winner in physics, 86 members of National Academy of Engineering, and 17 members of National Academy of Sciences. RPI graduates made instrumental contributions to many engineering fields, including the Apollo project for moon landing. The first speaker of this seminar series, Dr. Michael Miller, wrote a white paper entitled BME 2.0, and he mentioned in the paper, BME as a discipline emerged in 1960s and 1970s, led by several co-founding departments, including Johns Hopkins, RPI, and Duke. Our Biomedical Engineering department at RPI has produced outstanding results for more than 50 years. For example, the average number of research expenditure per faculty per year is over $400,000, and also the average number of journal papers per faculty member per year is over 8. Although we don't have a medical school at RPI, as our close neighbor, we have the world-class Industrial Medical Imaging R&D Center, which is widely known as GE Global Research Center, where Thomas Edison worked many years ago here. His desktop here is still on display as inspiration for engineers today. Well, so much about the introduction of RPI and the BME at RPI. Now we are ready to make the presentation. As I mentioned earlier, two parts, red part, research part, and the blue part, education part. Let's first talk about research, and the two parts in the research category. First, talk about machine intelligence for tomographic imaging. I'm sure many of you are familiar with Google Trends. I enjoy playing it at my leisure time. In comparison, artificial intelligence and deep learning attracted rapidly increasing attention since a few years ago. In particular, attention to deep learning exceeded that to medical imaging around 2016. So that will be a time point here. In 2016, I wrote a perspective article on deep imaging. We know AI, machine learning, especially deep learning, has been widely used in computer vision and image analysis. So image analysis, computer vision, goes from images to features such as segmentation and classification. On the other hand, tomographic imaging goes from raw data, tomographic data domain, to underlying images. So these data are features such as line integral or Fourier components. In the perspective article, we not only gave opinions, also we produced examples, and we did 3 experiments. The first one is low-dose CT denoising with deep neural network. So we have tomographic data, and we can certainly reconstruct images, and we can use traditional wavelet-based method to do denoising, like BM3D, and also we can do model-based reconstruction. And another way, and we use deep neural network in this domain, and we do deep denoising. So although the initial network is relatively simplistic, but still we get a very competitive results. Second example is on super resolution imaging. So the first column, you see 2 Sept phantoms. Second column, and you see Sept reconstructions after 20 iterations. So not many iterations, image look very much blurry. But if you keep iterating, you get much improved results. So third column, Sept reconstructions after 500 iterations, very clear. So what we try to do, so we go from this blurry image and to this label, so high quality image, and we link them with deep neural network. So the last column shows deep learning results. So this is a super resolution improvement. Our third example is on CT metal artifacts reduction. So you have this original Sept slice, and you have the metal shown as a blue block, and the metal will block X-rays, so you have missing data in the sinogram domain. You see it's missing data. And in numerical simulation, we generate a big data set, all kinds of metal parts. Then we train a deep neural network to estimate missing data in this metal trace. So this is a restored sinogram. Then we use filtered back projection to reconstruct a metal artifacts-free image. Based on the perspective article, we filed intellectual properties. April this year, and our US patent got formally issued. Although the IP was just issued, the priority date really traces back. So here you see the priority date, June 24, 2016. So I believe this is the very first IP quite general on deep tomographic imaging. I just mentioned in the perspective article, we gave 3 enabling examples of deep learning for CT imaging. So 3 examples are denoising, super resolution, and metal artifacts reduction. So let me show you initial effort in journal papers. So first 2 papers here by Chen and this by Kang and several co-authors. So these 2 papers are the earliest journal papers for deep denoising, CT denoising. And the third one by my student and collaborators, and we introduced the W-GAN and the VGG network. And the VGG network is used to measure perceptual loss, therefore monitor image quality in the loop. So see these images. You have full dose filtered back projection image, very good quality. But if you just use quarter dose, you have this noisy appearance. Even you use most advanced dictionary learning based low dose denoising, you will see residual artifacts. And with WGAN, advanced deep neural network, we got image quality visually very appealing to full dose counterpart. So this is a great result. Then we performed a high-level study, try to answer a strategic question. If deep learning approach is better or competitive with modern iterative reconstruction algorithms for low-dose CT. So basically, we collect all image data from major CT vendors like GE, Siemens, Philips. So all these images collected at MGH. Then we designed a modularized adaptive processing network. So we have several modules. We can just keep doing image denoising step by step. And we performed a double-blind reader study to see if deep learning performance is really better or worse than commercial top-line iterative reconstruction algorithm. So the results published in Nature Machine Intelligence and our data indicate that deep learning algorithm is comparable or superior to commercial iterative algorithm in majority cases. This high-level comparative study delivers a very important message. That is, deep learning approach is very promising for low-dose CT denoising. Think about this. And we just use modularized deep neural network for post-processing. If we could have access to sinogram raw data, and if we could combine model-based reconstruction method with deep neural network, the image quality could only be better. The first author of our paper is Dr. Hongming San, used to be postdoctoral fellow, now a faculty member with Fudan University. And he received, in this year's World AI Conference, he received Outstanding Paper Award. He is an outstanding researcher with a great future. In addition to deep denoising, we also keep exploring deep super-resolution imaging. For example, super-resolution microscopic imaging received a Nobel Prize. So we can ask an interesting question. How could we further improve the best optical super-resolution results? In that case, you don't have ground truth. Therefore, we have to realistically simulate numerical ground truth. And we did such simulation with point-like planar linear structures with clear biological meaning. In the left is just a numerical phantom we generated. And in the middle panel, we have a blurry, out of focusing effect, Poisson Gaussian noise, all incorporated into the simulation. So these are low quality images, and we have ground truth in the simulation. And by training neural network in supervised mode, so we have a super resolution network reported in this journal paper. And the super resolution results shown in the right panel. In our perspective article, we described a simple CT metal artifacts reduction experiment, where we use a deep interpolation network to fill in the missing data. Since then, many papers published on this topic. A most important paper, I would say, is Artifacts Disentanglement Network, ADN network, particularly designed to perform unsupervised metal artifacts reduction. Very impressive results. The key to unsupervised CT metal artifacts reduction is to have enough constraints so that the image reconstructed could be unique and stable. Along this direction, based on the ADN network, we developed this low-dimensional manifold-based disentanglement network. So this paper to appear in IEEE Transactions Radiation Plasma Medical Sciences. So basically, you see it's ground truth and this CT metal artifacts blue profile with filtered back projection. If we apply the ADN network we mentioned on the previous slides, you see major improvement, but still residual artifacts. Now we do unsupervised image reconstruction with ADN coupled with the low-dimensional manifold requirement. Then we see the image quality is significantly improved, and the blue and red curves almost overlap. We have discussed quite a bit 3 problems: denoising, super-resolution, metal artifacts reduction. Certainly, there are many other deep tomographic reconstruction problems, and a lot of problems can be revisited from a deep learning angle. We organized the very first special issue and for IEEE Transaction Medical Imaging in 2018. So we wrote an editorial, Image Reconstruction is a New Frontier of Machine Learning. I would say this special issue on deep tomographic imaging is very successful. Recently, I did a scopes search. The special issue published 3 years ago. Now the total number of citations is 2,400 something. The average number of citations per paper is over 100. As a comparison, and we look at another special issue published decades ago on compressive sensing for biomedical imaging. The total number of citations is 1,700 something. So average number of citations is comparable to a paper in this deep tomographic imaging special issue article receives. So comparable. But this compressed sensing special issue was published much earlier. Later this year, we will publish the second special issue on deep tomographic imaging. The total number of papers we received is about twice as many as for the first special issue. Now, IEEE Transaction Medical Imaging receive a journal impact factor slightly over 10, and partially due to hotness of AI-based imaging. So TMI now becomes a high-impact journal, and we will also publish an editorial for the second special issue. So far, I have been saying very positively about deep tomographic networks, deep denoising, metal artifacts reduction, super resolution. Now, let me say something about limitation or problems of deep neural network. Here is a landmark paper published in PNAS on instability of deep learning in image reconstruction and the potential cost of AI. The fundamental problem is adversary attacks that cause neural network unstable. So let me explain the basic idea. On the left, you have the original digit. Okay, you can have many images like this. You train neural network a classifier. You can have nearly perfect accuracy. Then we can use adversary attack algorithm and to compute this subtle noise we added on top of the original image. We got right image. For human eyes, no difference between left and right, and we know it is just digit 4. But for the well-trained neural network, they look hugely different. The trained neural network would report this number as 7, for example. So this means the deep neural network is not stable. In the PNAS paper, the authors reported that although their selected deep neural network are unstable, got all kinds of problems, but they used the conventional compressed sensing algorithms. And the compressed sensing algorithms would give you stable performance. So in a way, that's good news. The problem is solvable. Why deep neural networks would not give you stable performance, while compressed sensing algorithms do give you stable performance? And the author mentioned that this is due to so-called kernel awareness. Compressed sensing algorithm has built-in kernel awareness. In other words, relatively simple neural networks do not have so-called kernel awareness, but compressed sensing algorithms do have kernel awareness. And why not we just combine different algorithms together so we have the best from both worlds? Actually, this is indeed mentioned in the perspective article. So see figure 5 here. The figure 5, we have just the conventional iterative algorithm. We mentioned multiple possibilities, the green boxes, and to combine deep learning and the conventional iterative algorithms, including compressed sensing algorithms. Indeed, the integration of synergistic algorithmic element is a good way to go. So we can find the best solution in the intersection of these three spaces. The right space is space of data-driven solutions, reflecting deep image priors, so on. The green space is just the sparse solution space, reflecting so-called kernel awareness. Then we have this blue space constrained by tomographic measurement, respect data fidelity. So intersection of these three spaces is a solution space. The best solution should be in it. So we wrote a paper, a long paper, and on arXiv talking about stabilizing deep tomographic reconstruction networks using our so-called analytic and compressive iterative deep networks. We call it ACID. So you can read this paper if you are interested. That PNAS paper reported that some deep reconstruction networks subject to three kinds of instabilities. And the first instability is actually type 1 error. New artifacts can be generated, so called false positive. The second type of instability is just type 2 error or false negative, so small features can go undetected. And the third type of stability, when you have more data, network performance becomes compromised. So let me show you these two types of artifacts with deep neural network, CT network shown here, and MRI deep network shown here. With compressed sensing, we see and these type 1, type 2 errors are fixed. And with ACID, our network, and we can do even better. So type 1 error, see here, you got new artifacts generated. You see this block. So it's just something like a tumor, you may say, but actually just a text. So with deep neural network, and you got a problem. But with compressed sensing, you don't have this problem. And with this hybrid, we call it ACID and analytic compressive iterative deep reconstruction, and we get this even clearer. Okay, and the type 2 error, the green error, so missing feature. So this wing got disappeared, and this lettering, so just the invisible. But with compressed sensing, you can still manage to see the sentence. Can you see it? and with eyesight we can show it very well. So if you are interested in more detail, please read again this paper. And right now it's in fourth edition, and we keep improving this work. Deep tomographic imaging is not only about deep reconstruction. This is a green arrow from data to image. So think about what I commented earlier. So we know deep network to do image analysis, post-processing, so going from images to features. And also we can do kind of inverse process, going from features, tomographic features, line integrals, Fourier components, case-based data from feature to images. So if you have a network going from data to image, from image to feature, why not do this directly from data to features, potentially bypassing images? So this way, data to features is kind of something just end-to-end training. So this is what we are interested, and we actually filed IP, also received it just June this year, and this is end-to-end training doing deep radiomics analysis, and not from images, but we go this way from data to features. I coined the word radiomics to show radiomics can be done in the raw data domain. So this is the overall diagram. So traditionally you do tomographic reconstruction, and you can do deep reconstruction nowadays from raw data to images. Then you can perform image analysis or radiomics, and you can do a lot of important work, extract information, making final diagnosis. And radiomics means end-to-end from raw data, potentially bypass images. You reach final diagnosis directly. Deep radiomics can do great things. So recently, Professor Pingkun Yan's group, in collaboration with MGH, Dr. Kaura's group, and my group, we published a paper in Nature Communication. So what we did is to retrospectively analyze low-dose CT data. We know low-dose CT is for cancer, lung cancer screening, but we just twist the angle a little bit. We try to extract the information on cardiovascular disease, and we got very good results. So this is an example of radiomics. We believe deeper feature analysis can be directly performed in the sinogram domain. So my summer intern, Quinton, in collaboration with my group, Kernel and GE Global Research Center, we perform a feasibility study, and we try to extract features of cardiovascular blood vessel from sinogram data directly. And in sinogram domain, we believe motion artifacts will be the least. So we did numerical simulation, phantom studies, and we got this very good correlation between ground truth area size of blood vessel and the estimated counterpart. So if we can do radiomics analysis in data domain and in image domain, next step will be unification, both domain together, end to end. And certainly we need to be very careful about instability of neural network. So how to perform it well remains an open topic for research. For further information, you could just read this review article we published last year on deep learning for tomographic image reconstruction in collaboration with Professor Jungqiu Ye and Bruno Diemann. Early August, I delivered a plenary talk entitled X-ray Imaging Meets Deep Learning. This presentation contains complementary information to today's presentation, so you are welcome to take a look. We just covered the first point that biomedical imaging should be data-driven, intelligent, or smart. Now the second point, biomedical imaging should be hybrid for precision medicine and point of care POC. Multi-modality imaging is not new in medical imaging field. And you have several good examples. And PET-CT is the first example. So nowadays, in Department of Radiation Oncology, you won't see standalone PET scanner. Always you have this coupling, CT, MRI, and also you have Sept CT and Siemens pioneered the work, PET, MRI. MRI has great soft tissue contrast. And in surgical suite, you have multi-imagers together. You transport the patient back and forth. In medical imaging domain, we have three major modalities: CT, nuclear imaging, MRI. Multi-modality imaging, dual modality imaging, we see good example between CT and nuclear tomography, PET-CT, SPECT-CT, and also between PET, SPECT, and MRI. So there is no machine called CT MRI so far. So this is a missing link. Marriage between CT and MRI is among hardest. Say CT scanner and very active, high-speed spinning metal parts, acceleration experienced inside the CT gantry, maybe order of magnitude higher than what we had with space shuttle launching. So just too active. On the other hand, MRI scanner, you have this very strong background magnetic field, and we have this huge scanner, and we see it's just a major challenge to put these two huge guys together for simultaneous or concurrent CT MRI imaging. Whenever we have major constraints and we see opportunities to show creativity, and could we put just technically feasible put CT MRI scanner together? The problems I mentioned, the space limitation. So we could try interiorize CT and MRI, and we use lower field. So just try to put huge guys together. And also we have electromagnetic interference and high-speed rotating metal part and electron beam inside the X-ray tube, and all these things will mean a strong interference with MRI scanner, and the moving part will distort MRI field. B0 field is supposed to be very homogeneous, right? Even you can put them together, compromise a little bit both sides, then you couldn't get enough data as an individual scanner could collect. Holy grail of medical imaging would be, say, we call it Omni Tomography. So you have all imaging modalities together. CT, nuclear, MRI, ultrasound, optical, you name it. So put all things together. One scan, you got all information, diverse data set. So we call it all-in-one, all at once. Then the spatial temporal correlations can be well registered, and we can do deep radiomics analysis. So decades ago, we wrote this concept paper towards Omni Tomography. This is a toy example. So we have all medical imaging components built in, shown here, toy example. But it shows we could make them work together. In 2015, we wrote a Vision 2020 paper published in Medical Physics, and we advanced our toy design, and we show in particular simultaneous CT and MRI imaging would be possible and delivering practical performance like 0.5T, 0.3T MRI with interior X-ray imaging, and we have multiple X-ray sources around a patient. And in this article, we particularly argued the biomedical rationale why we want to do CT and MRI together. CT and MRI are very valuable tools for cardiac imaging. However, they have pros and cons. For example, CT is very fast, but soft tissue contrast is poor. And MRI delivers excellent soft tissue contrast, but will take long examination time. So with simultaneous CT and MRI, we could have their advantages combined, avoiding their cons. Cardiovascular disease is the #1 killer. Second killer is cancer. CT and MRI are also valuable for cancer imaging, particularly contrast-enhanced studies with CT MRI will help you reveal heterogeneity of the tumor. So we use CT and do perfusion study, use MRI to do contrast enhancement. The problem is that neither of them give you very high reproducibility. And we have intramodality, intermodality, intra-patient, inter-patient, all kinds of variabilities. But if we build simultaneous scanner, you get CT, MRI information simultaneously and will registered, and we have a possibility to dramatically improve measurement accuracy towards precision medicine. The overall vision for simultaneous CT MRI is very clear, but to my best knowledge, no company in the world has put serious effort to build such a hybrid imager. Why? I think the main reason is that the engineering undertaking is far from trivial, and the cost benefit, the profit margin, not very significant. Another angle to think about this problem is try to make a cheaper CT scanner, cheaper MRI scanner. Then we make a portable, cost-effective combination of CT MRI. And indeed, we have been very interested in making cheap CT scanner. And several years ago, we published a paper in journal X-ray Science Technology, and we got some news exposure. We try to make a simple CT scanner, linear scanning, and we estimate and scanner cost per unit around, say, 50,000, 10,000, something like that. And for past 2 years, we see a lot of news and generated by NanoX. They say they can make a portable tomosynthetic imager much cheaper, say 10,000, something like that. So you get these just field emission X-ray tube distributed along this arm. And here we have Professor Guohua Chao, a world-class expert in carbon nanotube X-ray source. So all these are interesting topics for further research. Related to this topic, and let me mention a multi-source imaging system prototyped at First Imaging. CEO is Dr. Yan Xi, and First Imaging is funding RPI, so we are working together. And the system is called Stationary Multi-Source AI-Powered Real-Time Tomography, so SMART. And this is a system diagram. And the multiple X-ray tubes and the detector pairs just distributed symmetrically. And if you count together, we have 29 X-ray tubes and 29 detectors. And we have all the X-ray beams on simultaneously. So data acquisition is in parallel. This represents the fastest imaging performance and ideal for cardiac imaging. AI-powered imaging and deep learning algorithm is used for smart system imaging. And we do integration of CS-based algorithm for sparsity promotion, and also we utilize deep image prior. So this is a network. So we have a trained unit, and we input noise to fit a CS-based reconstruction. As a result, we got pretty good performance. So this is a real in vivo study, small animal study. Few years ago, and we also published a paper. This is a conceptual design about a hybrid imaging system for simultaneous spiral MRI and X-ray scans. And as shown here, you have C-arm and also you have some permanent magnetic blocks to synthesize a background magnetic field, and you do C-arm scans, so you got two data streams for X-ray and MRI imaging. So this is a portable system, low field, and we can use MRI information to see neurological damage and CT information, see some metal part in it, like in the battlefield. So this is a low-end double helical imaging system. Now, all of the major medical imaging modalities are miniaturized, and we can consider a possibility to combine these portable images together for more information. So portable and lightweight systems are ideal for so-called point-of-care imaging. This is currently a hot topic at NIH, so we could do further research along this direction. While there remain opportunities for research on individual medical imaging modalities, and even more exciting are deep learning research for hybrid multi-modality imaging. A number of years ago, Professor Ding Shen's group wrote a very important paper on multimodality image synthesis. In this special case, we could predict CT images from MRI images, from low field MRI images to high field MRI images. Along this direction, and if we have multi-modality data set collected by different kinds of imagers, we can consider machine learning and deep learning to synergize this data set for best possible image reconstruction and radiomics. A company called Hyperfine produces low-field MRI scanners with background field only 64 millitesla, yet producing clinical quality images for various imaging tasks. So such kind of low-field MRI scanner can be combined with a portable X-ray, gamma-ray imager with robotic arm, C-arm putting together. This will be a portable simultaneous CT MRI scanner and not that costly, right? This could be feasible now. And we can put a portable imager on auto-driving car, and this is a part of future medical imaging, and we call it auto-driving vehicle-based affordable tomography analytics robot, Avatar. Avatar delivers imaging service wherever whenever needed. So this is decentralized medical imaging future, we believe. Let me make an analogy here. And we see two kinds of new human organ systems. The first one is iPhone. So iPhone is like our eyes and ears it receives and analyzes many kinds of external information, and emails, weather, forecasting, and your stock market, and so on. The other new organ system, I would say the portable system and the hybrid systems, and we mentioned earlier, and I call it imager. So the imager, like iPhone, also our extended organ system, but not like an iPhone type of thing, and we not focusing on external information. Imager helps map, analyze many types of internal features like anatomical, physiological, pathological, psychological. So imager, MRI, and CT, ultrasound, optical all together. So we can monitor ourselves constantly. And I hope in the future, not only Avatar delivers imaging service conveniently, maybe every family would have an Omni Tomographic system, just like your washing machine. Now we finish the first part on research. Let's move on to the second part on education. The educational part consists of 2 points as well. The first point is medical imaging course reformed in the AI framework. At RPI, we teach medical imaging at 2 levels, undergraduate and graduate levels. And today we mainly talk about graduate level medical imaging course at RPI. The prerequisite for graduate level course is certainly undergraduate medical imaging course, and we call it bioimaging bioinstrumentation, BIBI. So we use textbook by Dr. Webb, and we modified quite a bit. And the whole lecture posted online, you click this link, you see all the lectures. And the first part is really mathematical part because BME students are very diversified in background. So we need just to explain theoretical part a little bit so they know Fourier transform and so on. We would like to emphasize creativity education for graduate course. And what is creativity? So in Dr. Plucker's paper, this is a highly cited educational research paper. Creativity is defined as a product of originality and task appropriateness. So in other words, we think creativity, you need to have a novelty, and also your creativity should have utility. And how great your creativity is, that's a multiplication of depth of novelty and width of utility. So just some discussion about creativity. And we think how to increase creative potential. And that is a little bit different problem. And the potential, and we believe, is related to understanding of the material, and also you need a wide knowledge base, so you have many elements to do creative combinations. Okay, so BME is highly interdisciplinary, but theoretical, mathematical, physical depth, and could be sometimes a problem. In mathematical aspect, for medical imaging course, is very important. Unfortunately, many students are weak in this aspect. So linear system, Fourier analysis, sampling, those things are not well known to many students. So in the undergraduate level course, and we try to explain the Fourier analysis system. And we use this textbook prepared at Stanford, but this is for 1 semester double E student. This is too much for BME undergraduate. Based on that textbook, and we compress the material to about a quarter of that, so we can present the most essential part to BME student. We try to show students some types of material. For example, linear system, the definition seems very simple. So additivity coupled with homogeneity, or you put together, you have superposition principle. But really, we try to explain to students what's the relationship between this first line additivity, second line homogeneity. And we show sometimes from first one you can derive second one. From second one you can derive first one under different conditions. And also we show conditions, the first one does not mean the second one. And other conditions, the second one does not mean the first one. So you have a better understanding of linear system. Without a thorough understanding linear system, you wouldn't understand the safety invariant system. Then the convolution comes from that. And deep learning convolutional network is very powerful. So all the things demand thorough understanding. Then you become more motivated to do creative. After undergraduate biomedical imaging course, students got general knowledge. We move on to the graduate level. So we try to give thorough explanation of each major medical imaging modalities like MRI, nuclear. We try to give all the most critical ideas so students are well prepared. Before we introduce deep learning material into medical imaging course at graduate level, we already had a well-polished syllabus, as shown in this infograph. So we got a very high student evaluation for traditional stuff. But with deep learning playing more and more important role, we feel this is not enough. We need introduce deep learning into medical imaging graduate level education. In collaboration with Professors Yi Zhang, Xiaojing Ye, and Xuanqin Mu, we wrote a textbook published by IOP dedicated to deep tomographic image reconstruction. For medical imaging course, at a graduate level, we extensively utilized this textbook, and particularly the first part on neural network basics and the second and third part on CT and MRI respectively. In fall semester 2018, and we introduced a little bit deep learning. You see all these green titles, deep imaging, but not a major part. The major part is still traditional medical imaging material. In fall semester 2019, we totally reformed the medical imaging graduate level course. You see, from beginning, we talk about neural network basics and mingled with hands-on experience and all imaging modalities really with deep learning reconstruction built in. We have a experimental aspect of this course. So we allow students to do AI-based imaging hands-on. So we use Google Colab environment. Just so this book published by Xidian University, they also talk about experimental aspect of AI innovation. But all the examples are not for tomographic imaging. So in our course, we try to emphasize tomographic imaging. So that make our course quite unique. So we use Python, and the student can do programming. And initially, we try some simple things to understand the basic architectures, inner workings with simple examples. In the third class, students learn how to code the autoencoder. And the students try a little bit after sample codes. Then later on, they write letters on piece of paper, take an iPhone picture, and the network would be able to report what they just wrote. So they enjoy the experience. There are a lot of materials already in the classic medical imaging course. Now on top of it, you have deep learning. How to combine both of them organically is a real challenge. So our approach is to underline heuristic aspects of deep learning, such as adversary learning. For adversary learning, and we use a GAN network. So we have a generator and discriminator. So how to make your discrimination? So it's heuristically very clear. It's a statistical problem. Optimal generator is simply understood as a mapping from one distribution to the target distribution. Adversary learning process is best understood with a toy example. So this is one-dimensional distribution. So you have a synthetic south distribution and this blue target distribution. And we show students step by step how you alternatively train, optimize generator and discriminator. And step by step, we could have a pretty good performance. To promote creative thinking, we also covered some very innovative stuff, even not very practical. For example, this Nature paper is on polarized nuclear imaging. So a radio tracer like this red dot can be flipped around by magnetic field. So you have this radio tracer emission map. The probability of emission would be least around this direction, zero emission. So it wouldn't have signal. But along this direction, you have a lot of gamma ray photons received by this director. You can flip this voxel any way you want. So you can do innovative imaging. And in the Nature paper, it didn't consider radio tracer attenuation background. So we did some further work along this direction, see what would be a algorithm to recover emission transmission information altogether. So this is a model, so simple model. You have this voxel element, you can flip it, turn it on or off. So you turn it on with respect to left detector here, right detector here, the model. So M1 measurement will be emission. Okay, this emission source is subject to attenuation. And on the right, you have M2, the same thing. So you do the result and you do log operation. Then you perform first derivative, then you recover this mu, attenuation coefficient. Okay, so there are some interesting point to cover. And with this continuous formula, how do you do discrete programming? If the solution is unique, and how do you optimize sampling patterns? So all kinds of interesting futuristic things. By the way, if you do this well, you get emission, you get attenuation. Remember, you use magnetic field to manipulate these polarized tracers. You could do MRI imaging as well. So this will be another way to do Omni Tomography. Now, the last point, multi-choice testing in the pandemic. Education is a whole system. Examinations provides important feedback to optimize learning outcome. Traditionally, students take examination in a classroom. Instructor proctor them so that they can give answer honestly. Later on, we have multiple choice examinations. Students use a computer to answer questions. There are new ways for them to cheat, but we can still put students in single room with instructor to monitor them. In pandemic, situation is quite different. Students take examinations at individual home, and they have many ways to communicate, discuss, share answer via iPhone, email, so on. This is a new problem to solve. We develop a DOT system to meet this challenge. DOT means distanced online testing. This is a website you can click and try. Basic idea is explained in this diagram. So we gave students 4 questions out of 6 questions in a pool. And we group students into top, average, bottom 3 categories. And the students receive questions in different sequence. For top student, and they see student coming 1, 2, 3, 4. Average student 2, 3, 4, 5. Bottom student 3, 4, 5, 6. So the first question they see, they must answer within time slot 1. So by doing so, average and bottom student couldn't copy answer from first group top student. The top student only got limited time to answer their questions, so they do not have sufficient time to solve other problems. So after time slot, and they see new questions, and when the top student answer second question, know the answer, and the average student couldn't copy from the answer in the second time slot. So that's a key idea. The real problem is much more complicated than what I just explained. So we wrote this long paper published in Nature Partner Journal, Science of Learning, entitled Optimized Collusion Prevention for Online Exams During Social Distancing. So this collusion is a most important type of cheating that happens among fellow students. So the design can solve this collusion problem. And this is essentially a discrete optimization problem, computationally very involved. And we can also perform optimization adaptively, meaning that when students keep answering questions, we get data, and we dynamically optimize the sequence of problems. Throughout the pandemic, we have been using this DOT format for students in medical imaging courses to take their examinations, and we performed professional surveys, and the feedbacks from students are very positive, as shown here. So we ask students to answer questions in terms of sufficiency of time slot length, and convenience of platform interface, easiness of examination questions. Some students feel super difficulty. Some students feel super easy, but majority feel reasonable. So in the middle, okay. Also, we asked about similarity to other online examinations. So they are not the same, and we have time slot test to each question, and this is the mechanism. So we try to avoid collusion. This is our medical imaging course schedule for fall semester this year. So we haven't started yet. So we have introduction, the network basics, and we still do hands-on. From basic platform architecture, then we move on CT and MRI deep networks, and we also do a little bit image conversion, try to get some idea how to convert one modality to another. And we mingled classic medical imaging stuff and deep neural network imaging. So altogether, we hope prepare students well so they know both medical imaging and deep learning. So we have a middle and final examination. At this moment, we are going to do in-classroom examination. If situation changes, we will go back to use our DOT design again. As a professor, I'm committed to performing both research and education up to a high quality. Currently, I'm involved in co-editing a special issue for Technology and Innovation, which is an official journal of National Academy of Inventors. So this special issue has a theme, Artificial Intelligence Education, K-12 universities and beyond. So we hope to get good articles, and if you are interested, please submit to our journal. Deep tomographic imaging is an emerging field. A lot of papers already published, and many groups and many countries involved. I did a visualization of the whole field, and as you can see, United States and China play similarly important roles with international connections. And I hope we could collaborate on cutting-edge research and innovative education in this exciting field. So welcome collaboration. Well, so much for today. Thank you so much for your time and interest. Also, I'm deeply grateful for our funding agencies and companies, and most importantly, my students, postdoctoral fellows, and collaborators. Thank you so much.